Good to see you all. All right, well, we will start. We've got about 18 people now. People will be trickling in. And again, if you could put your name and affiliation in the chat, we'd appreciate it. My name is Stuart Coleman, and I'm the co-founder and executive director of VI, Wastewater Alternatives and Innovations. And we are an independent, a nonprofit that was founded in 2019 to deal with wastewater issues, and specifically the Hawaii's challenge of converting 83,000 cesspools by the 2050 deadline. And so we work on many different areas, but innovative technology and workforce development and water quality, education outreach, and financial resources, working with communities are some of the things that we tackle. And this is the second in our series, WISE Wastewater series, where we're highlighting really kind of innovative and practical solutions to our problems that can help us undertake these challenges and do it in a way that's better for the environment and more affordable for homeowners, communities, and the state. And so we are really pleased today to have our newest partner, Rob Kirshner, who's CEO of Innovatreat. And we knew we wanted to partner with some MBR companies and manufacturers. And when we met Rob, we knew he was the one, because he's actually designed the technology for other companies. And so we were like, let's go right to the source and find the person who has really kind of pioneered a lot of the treatment innovations that have happened with MBR technologies, which is one of the better ways of treating wastewater. And then he recently worked with Jeanette Laramie, who is a Kaimana, someone who's lived here for many years, grew up on the Big Island. She'll tell you more about that. Works with Sherwood Engineering. And so they partner on a really cool project, which I'll tell you about at the Theodore Roosevelt Library, using his technology. So we'll jump in right now. Thank you all again for joining us. And as we mentioned, this is what we have to deal with across the state: 83,000 cesspools, releasing 52 million gallons of sewage into our groundwater every day, with all kinds of risks to public and environmental health. And under Act 125, it mandates that all cesspools be upgraded or converted by 2050. And so with a minimum price of 20 to 25,000, our aim is to kind of reduce those. So I will hand it over now to Jeanette, who will talk about a little bit about their recent project. Thanks for joining us, Jeanette, and welcome.
Yeah, thanks so much, Stuart, and thank you just for the opportunity to present today. As Stuart mentioned, I grew up on the Big Island, so it's really special to be able to be here and just to share some knowledge and learn from you all as well. So Rob and I at Innovatreat, we've been collaborating for the last couple of years on a project in North Dakota, the Teddy Roosevelt Presidential Library, which just opened up about a month ago. Sherwood, the engineering company that I currently work with in San Francisco, we're the overall civil engineer for the project. So we led all of the site stormwater and also the design of the on-site wastewater treatment system. And then Innovatreat supplied the in-building MBR system, which Rob will explain more about in the next several slides. At this project, all wastewater generated on site is treated to a level that can be safely reused, both within the building for toilet flushing, as well as for irrigation around the site. And so, although this was developed for a much different context, obviously, than the situation in Hawaii, this type of treatment system is also very applicable for small communities that don't have access to larger municipal sewer systems. So this is, very similar to all of the small towns across Hawaii that are currently grappling with how to afford replacing over 80,000 cesspools. Can you go to the next slide? So the library is designed to integrate naturally within the landscape. This is one of the architectural renderings that was developed early on in the project. And as such, it was very critical for this project to be able to hide any sort of mechanical systems, including the wastewater treatment system, from any sort of view shed. And this was a key reason that we selected Innovatreat as the ideal vendor partner. So all of the biological process and storage tanks are buried at the exterior of the building, and the main MBR treatment system is external to those biological tanks, and they're actually housed in a mechanical room within the building, which is very unique compared to other MBR providers. Next slide. So the library had very ambitious sustainability goals, and this drove the selection of the on-site treatment and reuse approach. So the library is looking at the Living Building Challenge water pedal, which is one of the most ambitious sustainability certification programs currently. It requires a net zero water approach. And this image just shows another rendering of how the building kind of emerges from the landscape and the importance of really hiding everything within the landscape of the site. And next slide. So as a project site civil engineer, Sherwood designed all of the stormwater management and bioretention systems at the exterior of the building, including that green roof over the top of the building. This was to enhance the site's natural hydrological cycle and really emphasize infiltration rather than runoff. And we also partnered with Innovatreat to design the on-site water reuse system. As I mentioned, all of the building's wastewater is collected. It's treated on site to disinfected tertiary recycled water standards. This is the highest level of effluent quality. And then it's reused for toilet flushing within the building as well as for irrigation. And overall, this integrated treatment system is projected to reduce potable water demand of the library by over 50%. And now I will hand it over to Rob to really get into the details of Innovatreat's offering.
Okay, thank you, Jeanette. Just to quick summarize who we are. We're based in the Baltimore suburbs. The technology, the MiniMBR, as we call it, we developed that over the last 15 years. Initially, strategically to treat to super high levels of nitrogen and phosphorus removal because the Chesapeake Bay has been hampered by excess nutrients for decades. And the state of Maryland passed regulations and also, lucky for us, supplied funding, which I know you guys have been struggling with, that aspect. But one of the key factors to us having a pretty significant amount of success in reducing nitrogen and phosphorus as well was the funding mechanism. We lovingly referred to that as the flush tax, and that was passed in about 1990, 91. And it funded a tremendous amount of work throughout my entire career. I started in the mid 80s, and this technology was focused specifically on the smaller flows, which were kind of saved for last in the state's regulatory rollout. So we started delivering systems in the mid-teens. Our oldest plant, which was delivered in 15, is still running on the original membranes today, and it's hidden inside of a commercial building. Surprisingly, very similar to the way TRPL turned out. TRPL stands for Theodore Roosevelt Presidential Library. Sorry about that. It rolls off our tongue these days, right? Because we've been working on it for years. So just a quick synopsis then, as Jeanette described, the three red tanks are actually buried on the site. If you fly over the site with a drone or in an airplane, you can see just the manhole covers, and they're actually they're ductile iron, so they're rusted brown, and you can barely see them from even 30, 40 feet away. So it blends in nicely. Those tanks incorporate the biological reactors. Of course, all sewage is treated biologically. We're going to talk a little bit more about that in a second. but we provide something called equalization, which attenuates the flow going into the process so that we can optimize a whole lot of things. We can optimize the biological process, and then we also, of course, optimize the separation step, the membrane system, which provides for filtration of the biomass in the biological reactor, the, let's call it living soup that does all the work for us, that we oxygenate, aerate, mix, etc. And then the membrane system is optimized because it's not seeing big, huge spikes in flow that might occur during a wave of guests that visit the museum, the library throughout the day. It runs nice and continuously throughout the night because we equalize the flow, and that's why there's such large tanks for such a small system. This system treats about 12,000 gallons a day. Is designed to treat about 12,000 gallons a day. It sees a very varied flow. And I think the max we've seen is something in the neighborhood of about 6,000 gallons a day. That's equivalent, let's just say that's equivalent to about 20 to 40 homes, depending on the consumption in an individual home. But the equipment is staged, and you can see in the upper right corner of this slide, the equipment is staged in the utility room with all of the environmental systems, the HVAC systems, et cetera. They have geothermal heat and all the other cool features that are tucked away in the bowels of this incredible structure. Of course, it's really important that they're not noisy. There's no odors and smell, because there's a beautiful auditorium about, I don't know, 15 feet from this site where my equipment is, where they're going to hold presidential debates in the future. It's a really amazing bit of architecture. And in fact, I'm going to be there next week. I'm excited. I've been there before everything was complete. I'm very excited to actually walk through the museum myself for the first time. Complete, I should say. I've been there when it was being assembled. All of the systems, the power, everything is minimized to meet the living building challenge that Jeanette described. So, we're talking about a system that draws maybe 5 or 6 kilowatts of power while it's operating. It's very, very low energy consumption and producing, of course, extremely high quality reuse effluent. So what I'm going to, I threw this slide in because I want to very quickly explain for those who aren't, wastewater nerds like myself, and I hate to say, Jeanette, you're a nerd too, along with me. We get excited about this industry and this business, but you can hit me later if you don't, like that wastewater nerd conversation. We'll take that up over a beer. In any case, as you can see in the upper left, conventional wastewater plants, actually, we grow the bugs in the reactor, and then they separate the bugs from the treated effluent using Mother Nature or gravity. Then the clear water or supernatant leaves that facility. It's clean. Don't get me wrong. It's clean. It's pretty clean. Most big municipalities do it this way. Some provide sand filtration or some other sort of filtration on the back end. It's what most municipalities do. But when things are upset, when the bugs aren't happy, when toxicity hits for some reason, they get it upset, and you end up with excursions in the effluent quality. So the whole point of doing water reuse is guaranteeing high level of treatment. And that's why the selection for a system like this incorporates a membrane, a permeable barrier to separate the effluent. We went to great strides to develop the technology that you're going to see that, let's just say, does not look like the industrial equipment, tank, farm, whatever you want to call it, in this slide. The conventional plants of all types kind of look like that, and if we were building one in a nice neighborhood or in the scenery around the islands of Hawaii, oops, sorry, wrong way, we would not want it to look like that. My personal experience is that when we're working with developers, when we're working with homeowners, they don't want that in their backyard. It's just kind of an eyesore. Key to the technology, though, is in fact the membrane. And the membrane is also the, we'll call it potential weak spot in the system, because if the membrane permeability, the amount of water that can actually pass through this membrane, if that fails or fouls, you'll get no water out. The flip side of that equation is all of the water that does pass through is really clean water. So what we've done is we've taken a unique approach to the separation step in our process. And we've basically gone back to the roots of and the early technology developed for industrial separation. So this is a membrane, all right. This is not a typical municipal membrane. We took a robust industrial membrane that was originally designed for industrial waste separation, including oily, greasy waste, and repurposed it and operate it to separate the bacteria that we're talking about. Now, big plants couldn't justify this because of the relatively expensive cost of this type of membrane. But in small plants that we're talking about, the membrane is a small portion of the overall project. So getting the more robust membrane that lasts longer and can take more abuse is a huge advantage to the longevity and the operating costs and experience in the plant. So basically, we're talking about the separation being the most critical step. What we've done is we've extracted the membrane from the rest of the tanks, and that's why we're able to configure the plants in a very, let's say, attractive manner, but also in a much more efficient manner. So this slide describes the layout of what the typical systems look like. All of our systems, and frankly, all modern wastewater plants require some level of automation and controls. Our systems utilize an open architecture Linux-based system, which if you're a computer geek, you would understand that that's a non-proprietary computer technology. That means that it's not going to be obsolete in 10 years and software upgrades required, et cetera, et cetera. All of that is taken out of the equation by addressing that with a non-proprietary Linux-based computer control system, which is what we've done. Our systems are built in the factory actually right over my shoulder here, and that's actually a unit in the test bay, and that's a unit that'll do up to about 30,000 gallons a day. And you can see the two towers in the middle. Those are the membrane modules. All of the equipment, the pumps, the blowers for adding oxygen air to the biological reactor, the controls, the membrane cleaning system, which is all automated. We call it our membrane laundry. All of that is incorporated in a pre-engineered, pre-tested, prefabricated skid system. We build these systems, especially for these smaller projects like the decentralized ones we're discussing here. We build them with some unique features because we understand they're going to be remote. We understand they're going to be, let's say, visited by, I'm going to call it a circuit rider type operator. We don't have, like a municipal plant has a staff of 20 people running the plant 24/7. We don't expect that. So we need the automation to allow the run of the plant, 24/7. But when a blower fails or a pump leaks, we want to be able to service them quickly. So we'll have a shelf spare sitting in the room on a shelf, made to be very easily and very quickly with very simple tools swapped out. And within an hour of any piece of equipment having a problem, the system is back up and running. Of course, you get the alarm, you get the text message, and you're back up in operation in very short order. So the systems that we build can be configured in a number of different ways. You've seen the pictures of the one at the Theodore Roosevelt Presidential Library, but if we were building a plant that was behind I don't know, a warehouse or in the corner of a shopping center. We could deliver it in something that we refer to as a package plant. Now, our package plants are built built by us. Fabricated structures, however, are fabricated for us on the West Coast out of a technology called foam core fiberglass construction. Now, this construction method is pretty slick in that it is corrosion resistant because it's fiberglass. It's built in the method that mega yachts are built. It's a foam core vacuum resin transfer method of fabrication, and it's pretty slick because it's a monolithically cast structure that is insulated and it can withstand winds up to 160, even 200 if we want, 200-mile-an-hour winds. But we typically design for a standard 160-mile-an-hour wind. And in fact, we're building a plant right now for the city of Galveston. They have a park on an island in the Gulf of Mexico that has been hit multiple times with hurricanes. And we're building a special hurricane-proof version of one of these package plants for them right now. This is what one would look like. They're not very heavy because they're not made of steel. I mean, that thing right there that you see is about 25,000 pounds. If that was a steel package plant, that would be subject to corrosion, et cetera, painting. That would weigh double or triple that. And so it's fairly easy to handle, fairly easy to set and hook up, and corrosion resistant. I'll show you a couple of examples. That one right there will handle 50,000 gallons a day. That's a pretty large fiberglass structure, but in actuality, that entire structure takes up a 50 by 25 foot space. That's it. The underground tanks behind it there, you see the manhole covers, are the equalization and sludge holding tanks, where then they pull a truck in and vac out the solids and send it to the big municipal plant, 20 miles away. So the other facets that we like are similar to, again, Theodore Roosevelt. Theodore Roosevelt Library was a bit of a hybrid because it has a small tank that the membrane circulates on in the building, but the rest of the bioreactors are underground. In the case of this pole barn here that looks like a horse farm, it was built in the countryside out in the suburbs, beyond the suburbs actually of Baltimore, in horse country, where they raise a lot of racehorses. And so it was designed to hide in plain view in an area of a bunch of horse barns. This one is up behind that row of trees is an old folks home that's been there for about 150 years. Huge mansion. And all of their waste is treated inside that building. And you can see the tanks are completely sealed. Everything is vented to the outside. And that building right there treats 100,000 gallons a day of wastewater from a retirement community. This one here is, again, it's really pretty because it's just a simple shell. We dressed it up to look really nice, but inside is a 10,000 gallon a day system at this one treats wastewater from a firehouse where they have, firemen that are there 24/7, and a sports fields with a rest house for soccer and football and lacrosse and everything else. This is located about halfway between Baltimore and Washington. So I want to point out, we talked a little bit about the treatment plant structures, but what would be very interesting if we were to cluster a number of homes and drop small lift stations in where the cesspools are. They could be like an Aramco Prelos step system and low pressure sewers, which could then deliver let's call it solids less effluent, these effluent sewers, directly to the treatment plant. It would eliminate a lot of the screening and initial mechanical equipment. But if you had a grinder pump, we could handle that too. We have a screen system that could be integral into the system as well. Either one works beautifully. And the advantage of this low pressure sewer type system is you eliminate the deep excavation necessary for gravity collection systems and big pump stations. But you also can trench in small diameter, high density polyethylene pipe, 1, 2, 3-inch pipe that gets trenched in just below the surface. And it's a much, much more cost effective way of doing it. Now, we're not involved in that part of it, but that is a very complementary technology to ours. And why is that? Well, because we can deliver the system that looks like a little tiny, home, frankly. We could dress it up with windows if you want it. But basically that structure is 2 tanks, one tank having the screening, trash trap, sludge tank, equalization tank. The other side is the biological reactors. And in the dance hall in between is all of the equipment, potentially a battery if you want to run this off a solar and a power wall. And it could be then assembled into something that looks really nice. We can make the roof out of standing seam metal. We can make it out of corrugated metal. We can make it whatever you want, frankly, and it just drops right on top of the tanks. But it gives you full access, as you can see, to the equipment inside. It keeps all of the noise and equipment out of the weather, and it makes for a really nice neighborhood. Just to show you, we build bigger plants as well. This one is a 65,000 gallon a day plant that's been running since about 2019, direct discharging into the Chesapeake Bay. So this one's designed to meet total nitrogen down less than 3 milligrams per liter. That's extremely tight nitrogen limits, and 0.3 phosphorus. We've been achieving about 1.5 total nitrogen for that last 6 or 7 years. And we're also achieving a 0.03 to 0.04 phosphorus. So extremely, extremely clean water coming out of that. This plant was started up just 2.5 years ago. It's a 130,000 gallon a day plant at a new development on the Eastern Shore. And it's, as you can see, it has concrete tanks, larger bioreactors with hatches, again, vented to the outside. So it's a really clean environment inside that building. And it was donated by the developer to the town. The equipment is sitting right there next to the tank, as you can see. And my friend Tim is pushing buttons on the controls. That's what the computer looks like. Very clean, very quiet environment. And it produces exceptional. This one, again, has to meet 3 and 0.3. And this one's meeting about 1.5 and 0.02 phosphorus for the last 2.5 years. So in summary, the goals of the technology, and this is in no particular order, but we like the fact that it was aesthetically pleasing. That was important, not only for the neighbors, but when you have an operator running a plant that looks nice and it's nice and clean and a clean environment to work, they tend to take better care of the equipment, and it runs better when it's taken care of and maintained properly. And we make it easy for them to maintain it. They don't get upset at it, take care of it, and it runs better. It's just lower operating costs. We are capable of off-grid operation, which means we can run it on solar and batteries, if that was interesting to a customer and client. The membrane, because it's an industrial membrane built to operate at 100 PSI internally, and we run it separating little bacteria at 6 PSI. It is way, way, way stronger than necessary, and that's all in the customer's benefit. The membranes, our oldest plants today are 10 years old. They're not looking to replace their membranes anytime soon. So we're expecting 15, maybe more years of life on these membranes. The maintenance, of course, we talked about, very easy to do. It's designed to be easy. We designed it with operators actually cooperating with us and with them in mind. Of course, remote operability is very important. You can monitor the plant using your cell phone. Certainly, you can operate it through a secure VPN as well. If you have a key guy that needs to take charge of the plant, I can run it around the world, be anywhere, and actually dial in because it's run through a VPN. Obviously, low energy was a key. That was the driver. And we run the lowest energy of any MBR on the market, and we're about 30 to 40% less power than the next best system out there. But the last but not least, and it's kind of interesting for the Hawaiian market, we don't want to design systems where you've got to bury the tanks in rock. And that's a pretty important distinction. So we can run that system that I showed you by building everything at grade and hiding it in plain view. And that's critical to keeping the overall cost low, because excavation is a huge cost when you start digging deep holes in the ground.
Yeah.
Okay, with that, I'm going to turn it back to Jeanette because she's done some work in the neighborhood, and we're looking forward to doing that.
Yeah, thanks a lot, Rob. So I guess as a kind of final wrap up, this is a little personal for me. This is a couple of years ago at this point, but these are just a couple of photos that are close to home for me. So the one on the left is Puako Town on the Big Island. This is just south of where I grew up, and this is just really representative, as you are all very familiar, of many small communities in Hawaii that are too small and too remote to connect into a municipal system. But at the same time, upgrading individual household cesspools is sometimes just too costly for individual homes to be able to afford. And so, our thought is that this, a middle approach is necessary. So, something that's not at that large municipal scale, not at that individual household scale, but still fits this gap that's necessary to in order to be able to convert these 80,000 cesspools in the islands that are really causing significant damage to the environment. And then just at the center in the right, this is Pololu Valley, in the town that I grew up in, and here's with my son in Pololu. Just a constant reminder for me personally of why we need to keep doing the work that we're doing, finding appropriate and cost-effective sanitation solutions for our communities. So thanks everybody so much for this opportunity. And Stuart, I think I'll pass it back to you now.
Thank you, Jeanette. Thank you, Rob. And so for us, when we're looking, just as Jeanette said, we're looking for that, place in the middle, that sweet spot between large municipal systems, which have become just almost unaffordable, as we can see in the Hilo, renovations that are going forward at the Hilo plant. And then, the burden being on the homeowners to do their individual. And so we want to really start looking at decentralized treatment systems that are more affordable, that fit island geography better, and can really help more rural, remote communities, and fit in. And Rob showed you kind of just the structure of those. These are not your grandfather's wastewater treatment plants, the big industrial looking things that smell bad. I mean, they've really innovated to make them fit into a community. We want them to make them storm resilient. And there's a question in the chat that we can deal with that Stacy asked, about if it's going to be off grid, making sure it's storm resistant. And in light of the, Hurricane Lala and what's happened, that's going to be extreme off-grid capable, and not having the deep excavation costs that Rob mentioned, being able to pour a concrete slab and being able to just drop it in, kind of plug to play, and just more affordable and uniquely designed for each community. And so instead of having, a $40,000 cesspool conversion cost individually, these can be, through financing and through bonds and all kinds of financial tools, we can do these and just start with sewer fees and normalize that for everyone across the state. And making sure they run remotely and can be monitored remotely is going to be extremely important. And like we said, blends into the community. So let's give a round of applause for these guys, and then let's open it up for questions and comments for them. And we'll start with Ted's comment, and move into Stacy's about what are the upfront and annual maintenance cost of these systems, which is hard because they're so variable? And are there economies of scale for larger systems? I don't know.
Yeah, I can answer that by saying there are always economies of scale. So just for kind of a rough idea, a 10,000 gallon a day system and a 20,000 gallon a day system are pretty similar in price. You know, there's the 10,000 has one membrane module, the 20 has two. The tanks get a little bigger, so it's like almost imperceptible difference in price. So it does. There are breakpoints that are more, let's say, sweet spots, and the 20 to 30,000 gallon a day plant will treat something in the neighborhood of 50, 60 homes. So that is a sweet spot. Beyond that, it doesn't go dramatically higher. So you can go to the next level and it's maybe 30, 40% more, but you're doubling the flow. So, you know, we're talking about the equipment in the $1 to $3 million range, for a rough idea, up to about 100,000 gallons a day. So that's a lot of homes, and then the construction might add another million to two to that, depending on what kind of work has to be done, slabs and buildings and the sewers and things like that. So a lot of the work and a lot of the cost is really tied to the delivery to the plant, right? The getting the right of ways, and this is the stuff that Jeanette probably is much more attuned to than me, because I generally work on the plant, and then they'll design how to get to the plant.
Right.
Did that answer your question?
Yes.
Yeah, thank you. And before we move on to the next one about off-grid systems, and would this involve PV panels or similar, and making sure it's resilient with generators. Jeanette, did you have anything to add to that previous question or this coming one?
Yeah, and I think Rob pretty much covered it.
Yeah.
I'd say like a lot of it is just going to be really site dependent as well, especially with the sewer
Topography.
system and
Yeah.
everything. Yeah.
Yeah. Cool. So let's talk about the off-site, the off-grid systems and how they'd be powered.
Yeah, so PV would be really cool. During the day at the peak of my thoughts are that PV needs some space. So the bigger the plant, the more PV. Real small plants don't need a lot of PV for our systems. A backup generator is always, in fact, most states require a backup generator, so you're probably going to have one anyway, sitting next to the building in the corner somewhere. But the PV will most certainly feed a battery. If you have grid, and you probably have grid, the grid would feed the battery. The battery is going to get charged by whatever is available. If there's sun coming out, the battery is being charged by the sun. It turns off the grid. If the sun's down and you need more power and the battery drops to a certain level, the grid picks it up. And that's the best way to do it. It gives you resilience. We can also program the system to go into a low energy mode, because during a big storm event, you're probably not doing the dishes, running the laundry. And so we can run the plant at a very low energy and run the battery off the, to preserve the generator. There's a lot of things you can do with software these days that can extend the time of operation. So I guess, having said all that, if there's pump stations and they don't have backup generators, you're not going to get much flow. So this thing goes into a kind of a preservation mode. All of that is part of programming the system. It's very flexible. And like I said, it can be run 100% on solar. You just need the room for the PV, for the photovoltaic panels.
Great. Thank you, Rob.
Yeah, and I was just going to add to that, kind of similar to what Rob said. There's sort of smart ways that you can identify what are the critical power needs at a treatment plant for a certain period of time. Maybe it's a day, 2 days, And so for TRPL, for example, we have backup. The emergency generator supplies power to the lift station for sure, because that's a critical point at which we want to make sure that we're getting the sewage to those equalization tanks. And the tanks themselves are, I think we've got like 30,000 gallons of storage. So we've got enough storage to actually absorb about like 2 days of maximum flows. So that would be part of a treatment system, as well as supplying that storage. And I think we also have some of the blowers at TRPL. So just making sure that we're adding enough air into the system just to keep the biology alive until power is brought back on. So there's ways that you can sort of target the really like critical power needs in a system.
That's great. Thank you. And so the questions are lining up in the chat. This is great. Thank you for the really good questions, folks. Joey asked, could you talk about how biosolids are managed?
Yeah, real easy, because on this scale of a plant, we really don't want to manage the biosolids per se. We don't want to put in a process to treat them, to do any of that heavy duty, dewatering, et cetera. It just doesn't economically make any sense. What makes sense is to thicken it up, combine it with the screenings, and haul it away on a, let's say, monthly or every other month basis. So we size the sludge holding tank in a way that allows co-thickening with the screenings. It thickens up to about 3%. We have a quick disconnect hookup joint for a septic hauler to come in. They back a truck in, they take a couple thousand gallons and run it to where it can be handled much more economically, blending it with the big municipal system, on the other side of the island. And that might happen once a month by design. Generally, it's about a month as the most frequent. So we size the tanks appropriately. The bigger the plant, the more we have to consider it. So when you get up into that 100, 200, 300,000, that's a different story. That's not a cluster of homes. That's a town. And at that point, yeah, you're probably going to do something more focused, and that might be thickening, dewatering. There's small, scaled down technologies that we incorporate for that too. But that, in the cesspool situation, we're talking about more, let's say, spread out, more rural and clusters. You're not going to want to build a 100, 200,000 gallon a day plant and run, 6 miles of small diameter tubing. You're probably better off doing a bunch of little ones and taking those solids to the bigger municipality. I hope that answered the question. Jeanette, does that jive with what your thoughts are?
Yeah, definitely at these like smaller scale, like 10,000, 20,000 gallons per day. It for sure makes sense to haul away those biosolids. We've looked at on-site solutions for dealing with biosolids, and pyrolysis is one that we're super interested in. But we've seen just at like feasibility studies, around 500,000 gallons per day is where we see that start to become cost effective. So
yeah, I'll agree
one
with
day
that.
we'll get to do one of those.
Yeah, we built the first pyrolysis plant on the East Coast a few years ago here in Pennsylvania. That's 3 million gallons a day, and you get into that 2-3 million gallons a day, it starts to make economic sense. Anything smaller than that, it's going to be way more expensive than the treatment plant. Let's put it that way.
Yeah.
All right, cool. Thank you. The questions keep coming in, and when you talk about daily flows, maybe if you can mention like ranges of homes and such. Walker asks, what phasing advantages have you seen over cast in place concrete MBR systems or activated sludge plants?
So the phasing in terms of construction of parallel trains, I'm going to assume that's kind of the thought. We can do phasing with the number of skids, for example. We've done that on a number of jobs. So we can build the building with the tankage that can be, tied to another train added later and another skid added later. generally speaking, the preliminary treatment, the headworks we'll call it, can handle a whole lot more flow than we throw at it because it's a very compact thing. And then if you want to build it in a modular fashion and stage it, that is very easy to do. We can do that with fiberglass tanks. We can do that, frankly, we can do it with concrete tanks too. But I think to ship fiberglass tanks, we can get them in structures that are prefabricated, ready to go with the mixing and aeration system in it, up to 50 feet long. Now, that's not the easiest thing to ship around the islands, but we can make them smaller, 10 feet wide, 8 feet wide, 12 feet wide, up, 20 feet long, 40. It's very flexible. We are very flexible with the way we would stage that. And it would be fast because it would be factory built, tested, packed up, and landed on the site.
Yeah, ready to go, which is great, an advantage. Adam Reversi asked, how do you typically deal with required off-spec effluent storage?
Okay, well, that's a good question. Off-spec effluent in Maryland, there are shellfish protection requirements depending where you're discharging to. So if this is sort of a similar thought, in our area, off-spec water generally goes to a holding pond. Well, ponds take up a lot of space. Membranes and membrane systems, they don't do off-spec all that often. It's kind of, that's kind of the reason you go to a membrane system, because they generally, I think the line in the industry is the membrane systems don't fail qualitatively, they fail quantitatively. So if you've got a 20,000 gallon a day plant and you're not, and something goes wrong, you probably will have more frequent hauling than having bad water go out. I mean, so the environmental aspects aren't hampered. It's cost that ends up being your issue. Yeah, I mean, off-spec water is the question is what are we talking about? Are we talking about off-spec from a toxicity standpoint? Because that means somebody dumped something on you and no plant can survive that. And if that was dumped in a cesspool, that's going right into the aquifer, right into the coastal waters too. I don't know.
Maybe I could give an example just from TRPL. And I think it really depends on the context and what effluent quality you're trying to meet as well. For Teddy Roosevelt Presidential Library, the goal is to produce disinfected tertiary recycled water to be reused within the building. So there's a very high quality is required. And so for that particular project, we, because it's completely remote and offsite, there's no possibility to discharge to a sewer at all. We also have a backup leach field that's able to take 100% of the maximum daily flows. So our off-spec is there's a turbidity sensor. So anytime that is basically an indication of something has gone wrong in the system. So if the turbidity exceeds a certain threshold, there's an automatic diversion that then goes to the leach field. And that's really in place because we're trying to reuse this recycled water within the building. If there's not a reuse in place, maybe you don't need to have that, redundant leach field. Maybe that is your primary disposal. So it really depends on what effluent quality you're trying to meet. But that's one example of a way we've dealt with that off-spec effluent. Another example would be to divert it back to the equalization tank until an operator is able to get to the site and to understand what's happening with the system.
Yeah, the most cost-effective way to mitigate these kind of issues is to simply, and I say it simply because it's just money, right? It just costs dollars, but oversize the equalization tank slightly. I mean, if you've got a 20,000 gallon a day project, it's not a lot of difference between spending money on a 20,000 gallon equalization tank as compared to a 10,000 gallon equalization tank. They're not that different in a million system, right? It's
Mhm.
it's pennies, the difference. So err on the side of a little more volume because you can buy some time to react and do some things. And that's all part of it. And of course, the alarming system, the data that the system is giving the operators and giving them heads up to react, that's critical. Give them time to do something.
All right. Well, we have time for a couple more questions. If people want to put them in the chat. And one of them, Ted asked, what about the removal of PFAS?
I mean, that's a great question. I can answer that by saying these typical biological systems, PFAS goes right through them, including these type of membranes. I'm going to say that because the regulations yet are not in place to tell us to remove them. And in order to remove them, you have to actually go to RO if you want to filter the PFAS out. Now, there are a number of companies that have developed ways to remove the PFAS. We are partnered with a company called ECT2. They actually just got bought. I can't remember the name of their new company, but ECT2 makes a system that we could run our very, very shiny, clean effluent through because it won't see any solids. Will just selectively, using ion exchange, pull the PFAS out, and then the ion exchange media would need to be disposed of every 6 to 9 months, depending on how you size the reactors. That's one way. The other way, there's a technology that ECT2 developed and sells, and it's called nanosorb. And nanosorb are little tiny ion exchange granules that actually get fed as a powder into the bioreactor, mixed in with the biomass that grow and stick to it. And it absorbs the PFAS selectively so that when you waste the sludge out to the sludge tank, the PFAS goes out the door with the sludge and the water has no PFAS in it because the contact time in the biological reactors is frankly enormous, in terms of hours as compared to a filter, which is seconds. So you've got that way as well. Then it ends up as a disposal issue going out with the municipality. And then the economics make sense because the municipality, they're going to do something with their PFAS laden sludge as well. This is just going to add to that. So there's two ways of dealing with it. And those are the two most, let's say, cost-effective ways today on the market.
Great, thanks. Well, as we wrap up, is there one final burning question? I saw in the chat someone named Stuart Holmes raise their hand, but that's my middle name, so I don't know who else is in the chat. Was there another person that had assuming my identity? Well, I hope you enjoyed this, Rob and Jeanette. We really appreciate you presenting. I mean, this is just a whole different way to look at treatment, one that community members walking by might not even know that there's a treatment plan in there. And so I think that's very important, having the aesthetics and making it fit into a community, but also really just bringing down the cost, having the most efficient MiniMBR systems for these decentralized plants. During our previous wastewater webinar series, we had Rob Bolton talk about the Prelos model and what he had done in Vero Beach, Florida. It was just very effective. And now we're showing, okay, was the conveyance and now treatment. You can, combine these two things. We can cut costs dramatically, be able to serve some of these remote communities, make it much more resilient for storms, and then ideally for reuse. And so that's what we're really striving for. So we appreciate you kind of adding to this conversation. We will be sending this out, the presentation and the recording, to all the attendees and those who registered and who couldn't make it. If you want to share it with others, please do so. If you have further questions and want to set up any meetings with them, let us know. Or if you have ideas for future webinar series, please feel free to reach out to us. But yeah, Jacob, any of my staff, any other things you want to add? before we wrap up? All right. Okay. Cool. Well, thanks again. This is really exciting. Congratulations on the Theodore Roosevelt Presidential Library, the kind of to the highest standards in the country. It's really impressive. And we look forward to working with you and bringing these ideas and models to Hawaii. And thank you all for joining us. Yeah. We've got Jonathan Nagato from Department of Health, Gwen Yamamoto Lau from Hawaii Green Infrastructure Authority, Adam Reversi from Kauai. We've had a number of top engineers in the state, so we're really pleased that you all could make it today. And we look forward to seeing you at our next one. And folks from DHHL as well, I want to give them a shout out. Kelbert Yoshida at Department of Hawaiian Homelands. So thank you all for joining us, and we look forward to talking with you soon.
Thank you. Take care, everybody.
Thanks, Stuart. Thanks, Jacob.
Aloha.
Thanks, Jeanette.